variations not just on day-to-day scales, it turns out, but also on R-to-R scales. Okay? So there's something that gives off more light than billions of stars that is as compact as the size of the solar system, but somehow the other manages to change on timescales of ours. That's insane. That's absolutely insane. That's like saying that you have, an elephant or a dinosaur there that's dancing. Like, small things move faster, big things take longer to move. So to have this thing that's accreting and have it change in hourly time scales is crazy. It's absolutely insane. It's why I study them, because that makes them awesome in my books. Okay? So the question is that when you have nasty looking functions like this, how do you study them? Okay? So one thing that we can talk about is the color of this noise. Okay, so it turns out that noise comes in with many different colors. Okay? Can I ask you guys a question? Have you guys ever seen television on old-fashioned, analog cable on the CRT, right? And you've heard of white noise when you can't tune into any channel because your reception's all messed up and stuff. Well, this is what white noise looks like. Over here. Okay? White noise is sort of featureless. You have big values, small values, all coming in all the time. Okay? But you can have noise that has other colors, like for example, pink noise over here. Pink noise, what happens is that if you get a big value, the next value that you're going to get should also be somewhat large. And so there's a correlation between a value at some time and a value at some time later. Okay? If the correlations become even stronger, you can get something known as brown noise. Okay? And here in brown noise, you can see that you don't get this sort of very spiky tooth comb-like effect, but you instead get this nice big effect. Okay? So the way you talk about how the quasars varies, you talk about whether they look more like white noise or pink noise or brown noise, or even more tightly correlated noise patterns. Okay? Does that make sense? So now, what kind of instruments do you need to use to study quasars? Well, we had this instrument known as the Sloan Digital Sky Survey. Drexel was a member of the Sloan collaboration. Some nice people at the Sloan Foundation gave a bunch of astronomers a lot of money, and so we built a big telescope. We put it up in New Mexico, and for 10 years it took pictures of the sky. So unlike regular experiments where you know what you're looking for, in astronomy what you do is you take pictures of parts of the sky that you haven't looked at before, and you look for interesting stuff. And so one of the things that the Sloan Digital Sky Survey did, this by the way is the telescope, the Sloan telescope. It looks a bit funky, but that's just because the mirror is down here, and this is this very cool looking sort of shutter on the telescope. Okay? One thing that the Sloan Digital Sky Survey did is that it mapped out our universe. Okay? And this is a map of the universe where each of these little dots here in this fuzzy picture is a galaxy. Okay? So the thing that it answered is, what does our universe look like if you could stand back and look at most of the universe at once? Is it sort of evenly distributed as far as number of galaxies per unit volume goes, or is it sort of clumpy? And what the astronomers like my professor and Dr. Richards found is that you get these sort of clumps with filaments and walls of galaxies connecting them. And so they describe this by calling it the cosmic web. Okay? And this is actually very cool, because what you can do is you can look at this and you can compare it with what the universe looked like when it was just born. And you can ask, what combination of physics takes you from that very early universe to what we see right now. And that's the big thing that Sloan did. For the first time ever, we knew that the stuff that we see around us is just 4% of what's out there in the universe. And the remaining 96% we have no clue about. Okay, that's the dark energy, dark matter stuff that everyone loves to talk about. Okay? I'm not going to talk about that stuff because we don't know much about it. One thing that Sloan did that I found interesting is that there was this part of the sky called Stripe 82. And whenever there were clouds in the sky, and I don't mean like big, huge rain clouds, I mean like very thin sort of clouds that you wouldn't even think of as clouds. Right? Sloan went to this part of the sky and took pictures of this part of the sky. Because the one thing you don't want to do when you're photographing unknown parts of the sky is take pictures when they're clouds. Because then you don't know how bright things are. Right? So, but you don't want to waste the telescope time, so you go to a fixed portion of the sky and you take pictures there, hoping to discover changes. And it turned out that that portion of the sky had about 9,000 quasars in it. So that means that I have 9,000 quasars for which I have brightness measurements as a function of time over 10 years. The unfortunate thing is that I have, a measurement here, and there's a big gap of, a few hundred days, and then another measurement, then another one, and that means that the measurements are not very good as far as spacing goes. Okay? But you can do a lot of science with Sloan, and people have done a lot of science with Sloan, and one of the things that they found is that it's supposed to be the case that quasars really kind of like that, like brown noise. Okay? But this is based on very poorly sampled data. So what I did is I looked at another satellite out there called Kepler. How many of you guys have been following all the news about planets being found outside the solar system? You have? Okay. So a lot of those planets were found using the satellite called Kepler. And the idea behind Kepler is really simple. You point a nice telescope at a patch of the sky, you look for 4 years, and you look at individual stars, and you see if those stars, the brightness of those stars experiences tiny dips. And those dips come from planets crossing the face of that star. Okay, so if you see these dips and you see a dip every 3 years, you know that there's a planet going around that star with a period of 3 years. Simple, right? What that also means is that if there are quasars in this field, I now have very nice data for those quasars because it turns out that this spacecraft was in space. That's the name suggests. Okay? So as a result of this, I looked at Kepler, and all of those graphs that I showed you before come from Kepler. So with Kepler, you can get this very, very detailed time series for quasars. Now the sad thing about Kepler is that the people who launched the mission and had it funded by the government and stuff, they did not talk to people who studied quasars. And the way Kepler works is you have to say which stars you want to look at carefully. If you don't say that I want to look at so-and-so star carefully, Kepler just does not acquire data for that star, purely because of computational data transmission reasons. So that means that there are only 15 things that Kepler looks at that are quasars. That's sad, but I do get excellent data on those 15 things. Okay? So I have 15 such objects. I have data for 5 of them at the moment. Some more data should be available in April. So expect maybe another books and data store if you guys can. So now that I have these really high quality time series data, what do I do with them? Well, what I want to answer is, does the quasar variability stuff actually look like brown noise? Or is it that brown noise is simply a good fit for RADI data? Okay? And the way I do that is I look at something known as the structure function. But to explain what that is, the first thing I'm going to do is I'm going to do something very simple. Remember, I want to study correlations between what the quasar is doing at a certain time and what the quasar is doing 10 days later or 20 days later. So what I'm going to do is I'm going to take all measurements that are separated by the same time interval, and I'm going to make a histogram of them. Then I'm going to take all measurements that are separated by a different time interval, and I'm going to make a histogram of them. And I'm going to study these histograms as a function of time. So here are the histograms. Okay, this is the difference in brightness. It goes positive and negative because sometimes the quasar will become dimmer in the future, sometimes it will become brighter, and this is as a function of time lag over here. Okay, and this is just the relative frequency. And as you can see, if you look at points that are very closely separated in time, you have very tight correlation between the values. But as you go to larger and larger time scales, the correlations fall off until you get this sort of histogram that stays more or less the same. Okay? What would you expect for something like a sine wave? If quasar data came from a sine wave, what would you expect? You'd expect a big peak, right? So we don't see peaks like that, and this tells you that the behavior is stochastic, okay? That the behavior is all random and stuff. Now what I'm going to do is I'm going to take these first increments and I'm going to turn them into something known as a structure function. Okay? And the structure function tells me how much signal power I have for those of you who do signals analysis at a certain frequency. Okay? Before I do that, when I look at this histogram, one question that I asked that I thought was really interesting is, does this data come from a Gaussian distribution? Okay? And the reason why this is kind of cool to ask is because we all sort of tacitly assume that everything comes from a Gaussian. Now why do we do that? Does anyone know the answer? The central limit theorem. Awesome, good answer. Did you guys hear him? Okay, what does the central limit theorem say? The central limit theorem says that if you have 100 variables, and all of those variables come from distributions that have finite standard deviations, and I take the sum of those 100 variables, or 200 variables, or 300 variables, the sum will also come from a Gaussian distribution. Okay? So basically what I'm saying is that supposing I have my fist in the air, and I tell all of you guys to push in my fist in different directions. It doesn't matter how hard you guys push and what sort of distribution your pushes come from, as long as the variance of your pushes is finite. Okay? In that case, my hand will move as per a Gaussian distribution. Okay? And this is really useful because it allows you to sweep each individual push beneath the rug, and you don't have to worry about what each individual push is doing. But sometimes you get distributions that are not finite variance distributions. Okay, can anyone name one? Someone who's not a physicist, or maybe someone who's not a mathematician. Finite variance? The Cauchy distribution. Okay? So you do actually get distributions that have heavier tails, and what these heavier tails mean is that you get more extreme values. You get extreme values more frequently. And it turns out that if you have distributions like these, they don't sum to a Gaussian. In fact, you can get families of random variables that all sum to within that same family. So for example, here's in black we have a Gaussian distribution. You can see that the distribution falls off really quickly, and then as you vary the family parameter number, you get distributions with bigger and bigger tails. Okay, so you get this one's known as the Cauchy, this one's known as the Levy distribution. You can get any value between 0 and 2. So there are infinitely many such families. Now, do these actually show up in nature? Cauchys do, for example, in many places. The profile bits of spectral lines come from a Cauchy distribution, for those of you who do chemistry. Okay? So this is one question that I'm looking at is, are these distributions actually Gaussian, or do they come from something else? The other thing that I'm looking at is structure function, and unfortunately I have to cut myself short. If you guys pay attention this time, I won't have to repeat the introduction next time. But right now I'm finding that the structure function does not look like what SDSS data would suggest, and hopefully I'll give you guys a definitive answer in the next BNB talk if you guys want to invite me. With that, I will end, and thank you all for listening.
We're running out of time, so we've got about 5 minutes for questions. I'm not going to ask any, but you've got your 3 panelists up here. If you have questions for any of them.
Could we have the panelists come up to the front so that the audience could also see you?
If you can't remember their names, just say the one on this end and this end.
I have a question for the values. So one of the things we were talking about was the mindful consumer, and that it tends to be sort of a younger mindset. Do you think that makes a difference when you talk about the constituents that they're looking to target?
Oh, definitely. And you're exactly right. They are saying that that's something that's more of a millennial type of value system. So that's just another layer possibly for me to look at. Since I'm using kind of these aggregate indexes to for my indexes, like customer satisfaction is an aggregate of, it could include all types of ages of customers and their satisfaction. So that's a great another layer that I can take a look at it, age differences. Thank you.
On that note, how did you manage to, what tool did you use to analyze the content analysis?
Sure. I used a program called LIWC. They say Loop is how you pronounce the acronym. I think it's the Language Inquiry Word Count software. It's by Pennebaker. He's out of UT Austin. And you can use the software just as it is. That will give you the favorable, non-favorable analysis of text. But you can also create customized dictionaries to approximate whatever variable.
You probably heard about these recent within-mind problems, backing stuff. So, do you have any vision, any thoughts whether it's so construct line?
Well, unless the FAA says something, we don't know anything either. But yeah, they're still crashworthy. So as far as ISS goes, they're good. So they seem to crash it.
Can I ask him a question?
Sure.
Okay, so supposing I fly locally within the US, right? I can assume that there's not much luggage on the airplane. Where does the luggage get loaded first? The center of gravity, right? Where does that?
Yeah, that's a good assumption. Where exactly?
Yeah. In general, I mean, if I want to like, you know.
Maybe towards where the wing box is.
The wing box, okay.
Yeah, but the wing box also has a stiffer structure, so it might not be the best place to sit.
Yeah, I guess on a similar line, I mean, it looked like the luggage compartment was just modeled as just a single block of sort of mushy stuff.
Yeah.
Does that seem to be reasonably accurate, or did it seem to matter? Like, say you had one particularly like tall, hard thing, and would the person just sitting above that be out of luck, or?
So that basically, so the thing is with the test we had, the one data point, all the luggage was kind of just shoved in underneath the capacitive floor and strapped down. But typically in an airline, they put in the luggage containers and then put it into the subway underneath the capacitive floor. So that's a whole different issue. So since we only had that one test to match everything with, in the simulation, that whole mass of luggage was simplified into that one squishy block, which was modeled as a foam as such, with similar properties to how much load luggage could bear. NASA actually did a test on crushing luggage. And so when you lose your bags and you don't find them after a few minutes, I guess that's where it goes. So those are all still unclaimed luggage. So yeah, but yeah, that would play a huge, make a big difference in what kind of luggage containers you have and what other structures you have down there.
I have a question for the last speaker, actually.
Do you know my name?
I did. So why do you care whether the noise is brown or pink or white? What does that actually tell you about the reality of how?
So that's a great question. I was actually hoping to address that at the end. So remember, everything I've talked about right now is all data analysis.